Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum. Microwaves can pop your popcorn. They can catch you speeding. They carry thousands of phone channels to speed your calls. But can microwaves help us learn about our world and our universe? Let's find out. With wavelengths ranging from 30 centimeters down to 1 millimeter, microwaves fall between radio waves and infrared. Microwaves are used in Doppler radar, which is widely used for short-term localized weather forecasting and what you see on TV weather news. Satellites have revolutionized weather forecasting by providing a global view of weather patterns and surface temperatures. This unique perspective has greatly increased the accuracy of tropical storm and climate forecasts. Different wavelengths of microwaves, grouped into bands, provide different information to scientists. Medium-length, C-band microwaves penetrate through clouds, dust, smoke, snow, and rain to reveal the Earth's surface. Satellite microwave measurements reveal the full Arctic sea ice cover every day, even where clouds exist. These measurements show great variability from year to year, but also an overall decrease in Arctic sea ice since the late 1970s, illustrated here with maps and a time series of Arctic sea ice in September at the end of the summer melt. The Japanese Earth Resources satellite uses longer wavelength L-band microwaves for forest mapping by measuring surface soil moisture, such as this image of the Amazon basin, to identify areas of recent deforestation. L-band microwaves are also used by global positioning systems, such as the one in your car. Scientists routinely combine microwave information with information from other parts of the EM spectrum to study the composition of cosmic dust, or of a supernova, such as this supernova image that combines X-ray, radio, and microwave data. This recently known supernova in the Milky Way exploded just over 140 years ago at the time of the American Civil War. One important phenomenon is unique to microwaves. In 1965, using long L-band microwaves, Arno Penzias and Robert Wilson made an incredible accidental discovery. They detected what they thought was noise from their instrument, but was actually a constant background signal coming from everywhere in space. This radiation is called cosmic microwave background, and if our eyes could see microwaves, the entire sky would glow with a nearly uniform brightness in every direction. The existence of this background radiation has served as important evidence supporting the Big Bang theory for how our universe began. Microwaves have become both staples and wonders of modern life. They are also the backbone of communications and of Earth's sensing systems, and they are an excellent guide to the ancient history and origins of our universe.